We hear about the average all the time, right? The average salary, the average temperature, the average wait time. But what if I told you the average is, well, kind of lying to you? Today, we're diving into the secret life of data to see why the spread is often way more important than the center. And knowing this is going to help you make much, much smarter decisions.
So, let me ask you this directly. When you just see an average number, can you really trust what it's telling you? Let's look at a super simple business problem where you have two options with the exact same average, but one is a much, much better choice.
Okay, imagine you're running a business and you've got two shipping options on the table. Method A and Method B both have an average delivery time of 6 days. On paper, they look exactly the same, so it doesn't really matter which one you pick, right? But what if one of them is actually super reliable and the other one isn't?
Okay, so one of these methods is definitely the better choice, far more reliable than the other. But how could we possibly know that when the averages are identical? Well, to answer that, we have to look beyond the average. And this, my friends, is where the real story begins. See, here's the problem with averages. They only tell you about the center point of your data. They give you this one single number, but they tell you absolutely nothing about consistency or reliability. And a lot of the time, that's what truly matters. Is a delivery always around 6 days? Or is it sometimes 1 day and other times 11 days? The average alone will never tell you that. So the secret weapon we need to solve this puzzle, it's a concept called dispersion. It's just a way to measure how scattered or spread out your data points are. Instead of just seeing that one average point, dispersion lets us see the whole landscape. It shows us if our data is all huddled together, nice and tight, or if it's scattered all over the map. And really getting a handle on this spread is honestly a game changer. It's the key to making really smart decisions. It's what separates a risky bet from a sure thing, a reliable process from one that's totally unpredictable. So let's break down exactly why this concept is so important. So here's the main takeaway. Think of dispersion as a kind of trust score for the average. If all your data is in a tight little cluster, you can pretty much trust that average number. But if the data's all over the place, that average isn't telling you the whole story. This lets you compare how consistent two things are, and in worlds like business or finance, more spread almost always means more risk, period.
All right, so how do we actually measure this stuff? Let's start with the easiest one, the most basic tool we've got in our toolkit. It's called the range.
Let's look at a really simple example to make this concrete. We've got the exam scores for 12 students here. And you can see the scores are kind of all over the place, right? We've got a low of 10 and a high all the way up at 95. So how do we capture this wide spread with just a single number? So picture this. You have to describe that whole spread of scores using just one number. What's the absolute fastest, simplest way you could possibly do it? Well, the answer is our first measure. Boom! 85. That's our range. It's super simple to calculate. You just take the highest value in the set, which is 95, and subtract the lowest value, which is 10, and there you have it. It gives us a quick, single number to represent the total spread from top to bottom. Now, the simplicity of the range is both its biggest strength and its biggest weakness. On one hand, you can't beat how easy it is to figure out. But, and this is a big but, it's also really easy to fool. It literally only looks at two numbers, the absolute highest and the absolute lowest. It completely ignores everything else in between. So one crazy outlier can give you a totally misleading picture. We need something a little more robust. Okay, so how do we fix that problem? We need a measure that doesn't get so easily thrown off by one or two extreme values. We need to find the middle ground, where the bulk of the data actually is. So here's what we do. First, we take all those student scores and line them up from lowest to highest. Then we chop that data into 4 equal parts. We call these quartiles. Now, here's the clever part. We're going to completely ignore the bottom 25% and the top 25% of the scores. Instead, we'll just focus on the boundaries of that middle half, Q1 and Q3.
And this idea is the key to our next measure, which is called quartile deviation. Because we're only looking at the range of that middle 50% of the data, we've basically tuned out the noise from those extreme values at either end. This gives us a much more stable and much more reliable picture of the typical spread.
So for our student scores, we grab Q3, that's 71, and subtract Q1, which is 29. We then just divide that by 2, and we get our quartile deviation, 21. Now think about that. 21. That feels a whole lot more stable and representative than the 85 we got with the simple range, doesn't it? And this really gets to the heart of the trade-off, right? On the plus side, we totally solved our outlier problem. Awesome. But the downside is pretty obvious. We had to throw out half of our data to do it. So that leads to the next big question. Is there a way to get a stable measurement that also uses every single piece of data we have?
Well, it turns out yes, there is. So let's look at our final and probably most powerful measure. This is the one that gives us the full picture by taking every single data point into account.
This one's called the mean deviation, and the process is actually pretty straightforward. Step 1, you find the mean. The good old-fashioned average. Step 2, you go through every single data point and measure its exact distance from that average. And step 3, you just find the average of all those individual distances. That's it.
Let's use a new example here, this one about payments to 12 officers. So the average payment here is $1,351. Now we just do the work. We take the first payment, $863, and see how far it is from the mean. That's $488. We do that for the next one and the next one for all 12 payments. And when we add up all those individual distances, we get a grand total of 4,000.
Okay, we're on the home stretch. We take that total distance, 4,000, and divide it by our 12 officers. That gives us our mean absolute deviation, 333.33. Now this is a really useful number. It tells us that on average, any given payment is about $333 away from the mean. And the best part? We used every single data point to figure this out. No stone left unturned. So, let's tie this all together. Remember where we started? With those two shipping methods that looked exactly the same because their averages were identical? But now we have the tools to see the truth. By measuring their dispersion, we could easily figure out which one is actually the most consistent and reliable choice. There's a great quote that sums this all up perfectly. Dispersion is the degree of the scatter or variation of the variables about a central value. And that's the whole idea, isn't it? It's not about the center point. It's about the scatter. Understanding that scatter is the key to going from just looking at data to actually understanding.
So I'll leave you with this. The next time you see a headline or a report that just gives you an average, what's the first question you're going to ask? Hopefully you'll think, okay, that's interesting, but what's the spread? What's the dispersion? Because asking that question, well, that's how you find the real story hiding in the data.